So welcome to Math355 Abstract Algebra. This is lecture 23, and we're going to finish up talking about groups. We will discuss a problem that was mentioned last time, and then if there's time, which I don't think there will be, we'll talk a little bit more about other applications of what you're doing. So this is the end of the semester. This is the time when a lot of us are thinking about what classes to take next. And so I wanted to talk a little bit about a riddle, which is a great segue into a class I'm teaching in the fall on problem solving. But it's also important to be aware of how things are often presented. So do you know what a red herring is? So red herring is something that is deliberately misleading and is not related. And so the fact that I mentioned that this was related to a class I'm teaching, that's correct, but that is somewhat misleading as to why I am doing this problem. A good red herring is designed to fool you into looking at the wrong thing at the wrong moment. And so what I want to do here is I want to talk about why did I choose to do this problem at this moment in this class. So a red herring is to confuse you. Another term you might have heard is foresight, foreplanning, the art of a great lecture. This is where the professors spend months agonizing over every second of every lecture to make sure you're getting as much as possible. And we plan everything out so meticulously to maximize the value you're getting for your dollar. I could have talked about this problem anytime. I said I wanted to talk about it yesterday because of classes you might be taking in the fall. There's another reason I wanted to talk about it. What did we cover in Tuesday's class? What was the main theme? What objects did we look at? We were looking at permutations, and we're talking about how we could decompose permutations. So maybe this is a great example of an application of permutations. So much of how we attack mathematics depends on how it's presented. I'm telling you that we have a warden. There's 100 prisoners on death row. They're smart prisoners. They're mathematicians. Each one has a number 1 through 100. There's 100 drawers, and your number is in one and only one drawer. Each mathematician can open at most 50 drawers. If they see their number, they're saved. If not, they're killed. And in fact, it's even worse than that. Everyone must see their number for everyone to be saved. If even one person doesn't see their number, everyone is killed. So at first, it seems like the warden is just toying with the mathematicians. There's 100 of you. If each one of you just randomly opens 50 drawers, you have a 50-50 chance, a 1/2 chance of finding your number. So for all 100 people to be right, the probability of that with this strategy is 1 over 100. I'm sorry, 1 over 2 to the 100. That's like 10 to the 30. Now, more generally, rather than having 100 mathematicians, how many mathematicians should we have? No. In general, how many mathematicians are there?
In the world?
No. In a generalized version of this problem. This problem says there's 100 mathematicians, but more generally consider the case of n mathematicians. And we want to see, how does the probability of survival depend on n? Well, 1 over 2 to the 100 would become 1 over 2 to the n. This is dying exponentially quickly. Is it possible to come up with a strategy where rather than dying exponentially quickly, maybe you only die polynomially quickly? Maybe it's 1 over n to the 2024. That's still very bad, but it's much better than exponential. Maybe you can do even better than that and get 1 over log n. Or amazingly, maybe you can even do better than that and get a positive % chance of survival. And that's what we're going to show today, that there is a way to get a positive % chance of survival. And it's going to be a nice way to bring together a lot of techniques and ideas you've seen from several classes. Again, we're towards the end of the semester. I'm trying to choose problems that show you why you have spent the time learning the material, not just in this class, but in other classes, and just see how it all ties together. So if the mathematicians are just doing things randomly, we're in trouble. Let me rephrase the question to maybe guide you a little bit, to prime you in terms of how to look at this. The warden chooses a random permutation of 100 and uses that to assign the numbers. So if the permutation is 1 goes to 2, 2 goes to 5, 5 goes to 7. He'll put person 1's number in 2, person 2's number in 7, and so on. So now if I'm telling you that he chooses a random permutation, what theorems do we know about permutations? If I give you a general permutation, what do we know about it? We can write it as a product of cycles. So let's imagine prisoner 1 comes in, and prisoner 1 decides they're going to start by opening up the drawer with their number. And let's say they open 1. Oops, I forgot, I got to change the thickness. They open up 1 and they see a 3. And they open up 3, and when they open up 3, they see 7. When they open up 7, they see 89. When they open up 89, they see 34. When they open up 34, they see 11. And when they open up 11, they see 1. Person 1 is safe. They did it. Right? Success. Now it's person 2's turn. Could person 2, when they open up, drawer 2, could they see a 7? No, because we know 3 goes to 7. So it has to be a number that's not on my list. Maybe 3 goes to 4, goes to 5, goes to 6, goes to 87, goes to 88, goes to 90, goes to 99, goes to 98. What's the only way 2 is going to be in trouble? You're not answering. You're giving me the correct logic, but you're not answering the question I asked. I said, what's the only way that person 2 is in trouble? Right, and so what would have to be true about the cycle length for them to be in trouble? Right, so if the cycle length is greater than 50, they're in trouble. So in general, if the cycle length is greater than 50, or more generally, greater than n halves, you're in trouble. Is it possible to have 2 cycles of length greater than 50? No. So if I give you a permutation pi, I can write this as a product of cycles. So here, 1 goes to 3, 3 goes to 7, 7 goes to 89, 89 goes to 34, 34 goes to 11, not leave myself enough room, 11 goes to 1. Then I would have my next cycle, 2 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes to 87, and so on. And so as long as each cycle length is less than 50, we're okay. Is it possible that we could have a cycle of length greater than 50? Yeah, give me a cycle of length greater than 50. I'm sorry?
1, 2, 3.
Yeah, just 1 goes to 2, goes to 3, goes to 4. Perfect. So we know that it's possible. So how many permutations are there? So how many permutations are there? So we have 100 numbers. How many ways are there to permute 100 numbers? 100 factorial, right? Or n factorial in general. And what we want to do is we want to find the number of permutations with a cycle of length L greater than n halves, or L greater than 50. And if we can do that, then we can figure out the probability that you are in trouble. And the probability you're not in trouble is 1 minus that. So the probability you lose would be number of permutations, we will say a long cycle, over n factorial. The probability you win is 1 minus the probability you lose. So this is a great theme from probability. It's frequently easier to calculate the probability something doesn't happen and then take 1 minus that, or calculate the probability something does happen and take 1 minus that. Just which one is going to be the more convenient one. All right, so what is the probability? Have a cycle of length L with n objects. So I claim it starts off with a 1 over n factorial, because this is the number of possibilities, number of permutations of length n. Now, I have to choose a cycle of length L. And here, we will have L is greater than n halves. How many ways are there to choose the L numbers to be involved in the cycle?
Permutations or just L and?
Well, I just want to know how many ways can I choose the L objects, and then I'll worry about ordering them.
Yeah, it's N.
We'll use binomial coefficients. It's n choose.
N choose L.
It's just n choose L.
Yeah.
So this is number of ways to choose the L objects for the long cycle. How many ways can I order them? Nope. Almost. It's not L factorial. If you have a clock, how many ways are there to put the 12 numbers in the 12 spots in the clock? It's 12 factorial. But then you can always rotate it so that 12 is on the top. Another way of saying it is I can always start with 12, and then I have 11 choices of what comes next, and then 10 choices of what comes next. I don't have L factorial ways of arranging them. What do I have? L minus 1. Because it's a cycle, because I know it's a cycle. Now, how many objects are left? I started with n, I chose L, how many do I have left? And then I can order those any way I want as the rest of the permutation. And now I have a number of ways to order the remaining n minus L. Now, what's very important here is that L is at least n halves, because otherwise, if n minus, imagine L was like n thirds. So imagine L was like 30. Then I could have 70 objects left over, and I could have another cycle of length 30. And then the biggest danger in probability is double counting. I want to look at counting all the permutations that have a cycle of length 30. If I have 2 cycles of length 32, I technically have to count that twice, and I have to remove the double counting. We don't have that problem here because you can't have 2 cycles of length greater than n halves. So this is just going to be 1 over n factorial. N choose L is n factorial over L factorial n minus L factorial. We multiply by L minus 1 factorial. We multiply by n minus L factorial. And this is where you realize that we are living life well in terms of just the tremendous amount of cancellation. The only thing that's left is there's an extra factor of L in the denominator. It's just 1 over L. Everything else cancels. So the probability that you have a cycle of length L or with L greater than n halves is just 1 over L.
Where do we account for L? Oh, wait.
So here,
For every L.
we need L to be greater than n halves so as to avoid double counting.
Okay, yeah.
Very, very easy to make mistakes and stuff like this. But here, it's just really nice. It's 1 over L. So as one of my professors says, recall if you did not already know that the nth harmonic number is defined as the sum k goes from 1 to m of 1 over k. So the probability we lose is going to be the sum L goes from n halves plus 1 to n of 1 over L. That's the same as the sum L goes from 1 to n of 1 over L minus the sum L goes from 1 to n halves of 1 over L. And that's going to be the nth harmonic number minus the n halves harmonic number. Does anybody remember how the harmonic numbers grow? No, much, much slower than polynomially. Log. So the picture on the left is, I think, from Wikipedia. It's the probability distribution of the length of the longest cycle of a random permutation. And so the green corresponds to the survival probability of people. I'm not sure I entirely buy this picture. Oh, right. Because when you're less than 50, things are different. Because we were talking about the length being L. When L is at least 50, then it's fine. It's going to decay like 1 over L. Yes, that's reasonable. But for smaller values of L, it's much, much harder to calculate. Right, so we just need to calculate what's the area of the green, what's the area up to 50. We don't actually need the functional form of what the green is. Since we know the functional form of the red, we can actually calculate the total mass of the green, but we do not know the probability that the longest cycle is 30. That's a much harder problem, but we don't need to answer that. Only answer the problem that's asked. So you should know certain constants in mathematics. One of the ones you should know is Euler, or the Euler-Mascheroni constant. And it's basically the fact that the nth harmonic number, the sum k goes from 1 to n of 1 over k, is about log n. Better is log n plus gamma plus lower order. And the lower order is of size like 1 over n. So this is telling us that the harmonic series is growing like the log of n. I don't think there'll be time to prove that today. If there is, that's something we'll cycle back to. And what we needed to look at was we needed hn minus hn halves. So that's approximately log n plus gamma plus lower minus log n halves plus gamma plus lower. What's nice is we don't actually need to know what the value of the constant is because it's going to cancel. What's the difference of a log? The difference of two logs is the log of a minus b is the log of a over b. So the log of n minus the log of n halves is just the log of 2. So this is basically the log of 2. So the probability you win is basically 1 minus the log of 2, which is about 30%. It's absolutely amazing that the probability of surviving is so large. The initial naive strategy, you have a 1 in 10 to the 30th chance of living. The warden is toying with you.
For every n?
Once n is sufficiently large, once the harmonic approximation kicks in. And the error term here is of size 1 over n. So by the time you're at 100, yeah, this is really close to the answer. It approaches this answer very quickly. There's a lot of problems like this, where initially you have these naive strategies that give you really bad probabilities of things happening. But if you find the right way of looking at it, you can actually get a positive % chance. There's another problem of mine, problem that I love to do in probability. It's called either the marriage problem or the secretary problem, where again, it looks like you have an incredibly small chance of having something good happen. But it turns out you have a very high chance of something good happening. So there was a lot of really good ideas in this problem. The first is trying to figure out how should we look at it. And if we use different phrases, if we try to put things into math speak, what is the warden doing? He's choosing a permutation. And the question is the warden just putting things in randomly? If so, then that's a random permutation. And we might be able to exploit that. And so we were then able to use some of the material we had learned this semester on cycles and apply that result. Now, to finish the analysis, we had to use some combinatorics. We had to use some things about the properties of the binomial coefficients, which we've seen in Pascal's triangle. We've seen identities related to binomial coefficients. We've seen combinatorial interpretations. And so to write things down, we then used our combinatorics. We got the following formulas. We expanded things out. And then we were lucky that everything canceled so nicely. And you get a 1 over L. And then this just comes down to the harmonic numbers. And there's beautiful formulas to give us estimates for the size of harmonic numbers. And the final answer is just absolutely stunning. About a 30% chance of surviving.
Why is the picture showing 2% max though?
Well, think about it. When L equals 50, 1 over L is 0.02. And then that's why this is the probability of the length of the longest cycle. So
okay, that's
so in some sense, what this is saying is that the cycle length that has the highest probability of being the longest length is 50, which is not immediately clear. Okay. So what I want to do now for the remainder is I want to turn to, oh, interesting. It seems to have rescaled the window. I'm not going to fix this in real time. Nope, I will fix it in real time. Okay. Is talk about one of the beautiful decomposition theorems we have. So there's lots of different ways of writing things. And this is the advantage of lecturing like this, is I can actually just toggle back to Thursday's lecture where we ended on the structure theorem for finite abelian groups. And before that, we had talked about the classification of finite simple groups, and things get really complicated in terms of what the possibilities are. But simple groups, finite simple groups, are basically the building blocks for finite groups. The situation is a lot nicer if we happen to have a finite abelian group, so things commute. The result is that in this case, you can write your group as a product of cyclic groups, or if you want, as a direct sum of cyclic groups. We often write abelian groups additively, not multiplicatively. We could write them multiplicatively. Why do we avoid multiplication? What set has multiplication as an operation but is not commutative? Matrices. And so because of that, we typically use addition for situations where we know things commute. We don't have to. We can introduce a new symbol. We can introduce, the symbol star and say, I'm going to use star to represent my binary operation. But as a convention, we typically use the plus sign for things that are abelian. We could still use the multiplication sign as well. And here are two different ways of writing our group as a product of cyclic groups. One is the indices, divide the next one. And then the other one is we have, prime powers. And depending on what problem you're looking at, sometimes one decomposition is a little bit more tractable or easier than another. And so for situations like this, you have to figure out which way do you want to write things. Right now, I'm just more concerned with just there is a way. Okay, so let's go back to, so the fundamental theorem is that we can write every finite abelian group as a direct sum of cyclic groups. So what do I mean by direct sum? So you should have seen this a little bit in some of your previous classes, maybe multivariable calculus, but they might not have emphasized the language. So if I give you two abelian groups, big A and big B, I can form a new group, big A plus big B. And that's going to just be the set of all ordered pairs, little a, little b, where in a shock, little a lives in big A, little b lives in big B, and the way I add pairs is I add them component-wise. You've seen this before when you've done things like R2, R3, or if you had a good multivariable class, Rn. Just looking at n-dimensional space and just adding things. And there's frequently more than one way we can write things. And the question comes down to, how do we want to write things? So for example, let's imagine I give you an element such that a to the 7th is the identity, and another element such that b to the 5th is the identity. So I can have the set generated by a, which is going to be 1a, a squared, dot, 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 a to the 6th, and the set generated by b, which is going to be one b, b squared, b cubed, b to the 4th. What's the order of a? So what's the smallest power? It's going to be 7. What's the order of a squared? 7. By Lagrange's theorem, any subgroup has to have order dividing 7. Right? What if I told you a to the 6th? Well, if I gave you a to the 6th, it would be very different. So order of a is 7, as is the order of a to the k for any k not equal to 0 mod 7. What about the order of b? So what would the order of b equal? 5. And again, as is the order of b to the k for any k not equal to 0 mod 5. So this would be very different, note, if c to the 4th is the identity, then the order of c equals 1, equals 4. What would be the order of c squared? 2. What would be the order of c cubed? 4, because, c cubed is not the identity. If I square it, I get c to the 6th, which is the same as c squared, not the identity. If I cube it, I get c to the 9th. That's the same as c, not the identity. The only thing left has to be 4, because it's got a, and you can see c to the cubed to the 4th is c to the 12th. The other thing is, I know c cubed is not the identity. So by Lagrange, it has to divide 4. So it has to be either 2 or 4. So as soon as I know that c cubed squared is not the identity, I know that c cubed has to have order 4. So let's consider the set of all things of the form a to the m, b to the n, 0 less than equal to m less than 6, 0 less than equal to n less than 4. I can look at this set. I claim that this is really like the direct product of these two cyclic groups. Because if I multiply something in the cyclic group of A and something in the cyclic group of B, because they're abelian, if I'm assuming abelian, so we assume abelian, so AB equals BA. So whenever I do my multiplications, I can always just group all the powers of A together, all the powers of B together. Is it possible, could A to the M1, B to the N1 equal A to the M2, B to the N2? If yes, then I would have A to the M1 minus M2 equals B to the N2 minus N1. Is it possible that some power of A is equal to some power of B? So could I have some power of A equals some power of B? Why not? But there, so is there any element in common with the cyclic group of A and the cyclic? One, right? Any two subgroups of the same group have to have the identity in common. So is it possible that a power of A could equal a power of B? Yes. The only way this can happen is we need M1 to equal M2 and N1 to equal N2. So as long as we restrict ourselves to M and N in the ranges specified, there's no way that I can have two of these elements being the same. So these will all be distinct elements. If the order of A and B were not primes, then things could be very different. But here I know A and B are two elements of prime orders, the different prime orders, so I can't have any repeats other than this. When you're trying to analyze groups, if the group is small, there's not too many possibilities and things aren't so bad. As the size of things get larger, it becomes much harder. So over here, there's lots of ways I could write it. I could write it as a direct sum. Maybe all things of the form IA, comma, JB, 0 less than or equal to I less than 6, 0 less than or equal to J less than 4. Less than or equal to 6, less than or equal to 4. And that should have been less than or equals earlier. But of course, it's really redundant to be writing the A and the B. I should really just write it without the A and the B. Just write pairs I, comma, J with 7, 0 equals 0, 0 and 0, 5 equals 0, 0. And I can view all of my numbers, A, M, N, just as a pair M, N. And I'm just doing addition on clocks. The first component, it's a clock with 7 hours. The second, it's a clock with 5 hours. Okay, so what I want to do now is I want to go through a proof that every finite abelian group can be written as a product of cyclic groups, or a direct sum of cyclic groups. And so I did some searching on the web, and the reason I want to do this exercise, and I debated putting this on the exam, is this is what you're going to have to do later in life. You're going to have some technical material that you need to learn. You're going to do some searching, and you're going to try to see, can you learn from this? Can you trust it? Does it have all the steps? Are there anything that need to be completed? I remember years ago, I was teaching at Princeton, and I needed a proof that either E or pi was transcendental. And it's a standard argument, and I knew I could find it online, and I found it online. The person who posted the proof also posted a 4-page proof of Fermat's last theorem using entirely elementary methods. That doesn't mean that his posted proof of the transcendence of pi is wrong. It just means I'm going to be really careful looking at it. The proof turned out to be correct. I am kicking myself now. A couple of years ago, I was in South County, and there was a beautiful sign that you could buy with one of Abraham Lincoln's most famous quotes. And it was something along the following lines: the problem with the internet is you can't trust everything you read on it. A. Lincoln. And again, just because something is posted doesn't mean it is correct. This is a philosophical thing to think about for mathematics. Mathematics is a lot more inclusive now in that it is very easy for people to put things out there. And because of how easy it is to use LaTeX, you can put things out there that look nice. Can you trust what you put out there? And so there's a huge conversation you can have about who should be the gatekeepers. Should you just have everything out there and then it's up to people to read and check things well enough to trust it? So let's go through this proof. So I'm first going to read the proof mostly without too many comments, and then we'll go through it line by line and see if we buy it. And if we don't buy it, can we fix it, or can we addend to it? So the proof is the following. Choose the n to be the smallest integer we can, such that G can be generated by a set with n elements. Right now, we're just trying to make sure, do these sentences sound like things I can check? Do they sound true? Among all generating sets with n elements, choose one containing an element x1 of smallest order k. So that means if you look at any other set of size n that's generating, it will not have any elements of order smaller than k. It might have elements of order k, but it won't have anything of smaller order. Let H be the set generated by the elements x2 through xn. So we take our generators, we ignore x1, and look at what the others generate. The claim is that H is a proper subgroup of G by the minimal choice of n. And since H is abelian and it has strictly smaller size than the size of G, by induction, we can write H as a product of cyclic groups or a direct sum of cyclic groups. So we now claim that we can write G as the sum of the cyclic group generated by x1 and H. We're not saying that H is generated by x2 plus x3 plus x4. We're just saying the sum direct sum of cyclic groups that give us H. So we claim G is the direct sum of x1 and H. It suffices to show that the only element in common between the cyclic group generated by x1 and H is the zero element. We know they have to have the zero element in common because they're both subgroups. And the claim is that that's the only thing. If it wasn't, then this would violate, G would not be a direct sum. We would have multiple ways of writing elements. All right, so how do we show that the intersection is just the zero element? Well, assume we have some element z in the intersection and assume z is not zero. Then we can write z as some multiple of x1 because it's in the cyclic group generated by x1. And because it's not zero, we can't have a1 equals 0 or k. And then we also can write z as the sum of multiples of xi for I going from 2 to n. Okay, and so now if we let the GCD of the a1 through an be d, what we can do is we can take the two expressions for z and subtract one from the other. That's going to be 0. And then we can divide everything by d and we'll still have integers. And we'll call that element g. And so the order of g is smaller than k because if we take g and add it to itself and we have d times, then we know that's going to be 0. And so since d is smaller than k, we've just found an element that has order less than k. This almost violates the minimality. We assumed of all sets of size n that generated that we chose one where x1 had the smallest order. We need to just show that we still have a generating set. So we want to replace x1 with g and say that g, x2, x3, all the way up to xn generates. And the reason this is true is because the coefficients a1 over d dot 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 an over d are relatively prime. So by the lemma, replacing x1 with g is still going to generate. We can make that replacement. But now we have a generating set where the order of one of the elements is less than k. That's a contradiction. So does anybody see the mistake? Or the gap? If not, we'll go through it carefully, slowly, line by line. All right, let's go through it carefully, slowly, line by line. So let's look at the proof. So we choose this an n, and we'll choose the smallest n such that G can be generated by a set with n elements. So the first thing is, can you find a set that will generate G? Is there at least one set that generates G? Yes. So good. G, whoops, I don't want to keep it. G generates G. So at least one generating set exists. how many subsets does G have? Okay. Or how many non-empty? So how many non-empty subsets? And the answer could involve the size of G. Yeah, so give me an answer as a function of the size of G. Good, it's just 2 to the number of elements in G minus 1. For each element of G, we either take it or don't for our subset. So there's 2 to the number of G subsets, but one of those subsets is we never took anything. So the number of non-empty subsets is 2 to the size of G minus 1. Yes? So no, not saying subgroup. This, you could also do it if you want to do a longer calculation, as it's the sum, L goes from 1 to the size of G of the size of G choose L. And what we're doing is we're looking at how many subsets of G are there of size L, and we add up all the different possible values of L. And we exclude L equals 0, because then that would be the subset of no elements. So there's only finitely many. This is a finite number. So since it's a finite number, can we look through all the finite numbers and see which ones generate G? Yes, there's at least one that generates G. So we can find which set of elements which generate G have the fewest number of elements. There could be many of them, but we can find it. So because everything is finite, it may take a while, but we generating sets with the fewest elements. Okay, so I'm not saying I can do this in any reasonable amount of time. You know, the universe may die, the heat death several times over, but it's a finite calculation. Once we have all the sets of size n that generate, for each one of them, I can look and see what is the order of your smallest, what's your smallest order? Maybe it was 6 for the first one, 8 for the second one, 7 for the third, 23 for the fourth, 5 for the next. Okay, now 5 is my new smallest order. And I go through the finite sets and I see what's the smallest order observed. So can find, you know, the K, it's a finite search. So everything here is, you know, it's a well-behaved finite search. We're okay. So everything here is fine. And so we've now shown that there is an n. It's the smallest n that works. There's no set with n minus 1 elements that generate. And x1 has order k, and no generating set of order of size n contains an element of order less than k. It might have an element of order k, but it doesn't have anything with smaller order. So we're doing another minimality argument. Okay. Next part. If H is the set generated by x2 through xn, then H is a proper subgroup of G. So the first thing is, because we chose n to be the smallest integer such that G could be generated with n elements, we only have n minus 1 element, so it can't generate all of G. Cannot generate all of G with n minus 1 elements. So H is a subset but not equal to G. Okay? Then we just have to prove that H is a subgroup. So now just, you know, prove H is a subgroup. Okay. And then you basically just have to say, if I have a linear combination of the x's with integer coefficients, if I add 2 of them, I still have something of that form. It's associative. I have the identity. I have inverses, because each one of these elements has finite order. So it's not bad to just go through and verify that H is a subgroup. And now, by induction, we know since H is a proper set, it has smaller size. So H, a proper subset of G, implies that the size of H is less than the size of G, so it can use induction. So we know that H can be written as a direct sum of cyclic subgroups. Okay, so far so good. Next part. We claim that G is equal to the direct sum of the cyclic group generated by X1 and H. And to do this, all we have to do is we just have to show that the intersection is 0. Is 0 going to be in the intersection? Yeah, they're both subgroups of G, so they both have to contain 0. Okay, so we know 0 is in the intersection. We just want to show that there's nothing else. And then clearly, when we look at the combinations, when we look at the sums, we're clearly going to get all of G because we now have X1, X2, X3 to Xn. So it's clear, get all of G as we have X1, X2, ... Xn. Okay. So now, here's the main step. So imagine we have some Z that's in both. So because Z is in the intersection of X1 and H, we can write Z as A1, X1 with 0 strictly less than A1, strictly less than K. And we can also write Z as the sum I goes from 2 to N of AI X sub I. Because that's what it means to be in H. So we have two different ways of writing Z. So if we subtract them, we have to get Z minus Z, which is what? 0. So Z minus Z equals 0. So we get negative A1 X1 plus the sum I goes from 2 to N of AI Xi. And now we're going to let D be the greatest common divisor of the A's. A1 ... AN. And so this 0 is actually equal to negative A1 X1 plus ... And if we divide by D, what's 0 divided by D? It's still 0. Negative A1 over D X1 plus the sum I goes from 2 to N of AI over D Xi. And the AK over D are integers and relatively prime. Right? They're relatively prime because we removed the common divisor. So we're going to call this element G. Do we know that G is 0? Well, let's think. If I give you the ring is Z mod 12Z, and I tell you 6x equals 0, does x equal 0? No. It could be 0. What else could x be? It could be 2. It could be 4. It could be 6. It could be 8. It could be 10. So just because the sum is 0, when I divide by D, I'm basically asking for what number, when I add it to itself D minus 1 times, is going to give me this. I don't know that G is 0. So G might be 0, might not. However, DG is definitely 0. right? And so the order of G is equal to D is less than K if G is not 0. Because we just showed DG, actually, I shouldn't say the order equals D, it's less than or equal to D. So it's very easy to make mistakes when doing this. I just know that D copies of this gets me 0, but maybe I don't have to do D copies. Maybe I could do a little bit less. Okay, so we have an element G. Its order is strictly less than the order of K. And then the argument ends, by the lemma as the coefficients are relatively prime, G x2 ... xn generates the same set as x1, x2 ... xn, but now have a new generating set with an element of order less than K contradiction. So that's the last line of the proof. Do we trust this argument? By the lemma, as the coefficients are relatively prime, G x2 through xn generates the same set as x1, x2 through xn. But now we have a generating set of size n with an element of order smaller than K contradiction. Yeah, exactly, right? By the lemma. Okay, what lemma are you using? So the person who posted this, again, it was a very nice service to post this, did not post the lemma. So there's a lemma that's implicit here. And let's see, implicit is, oops. Just trying to close the window. Okay. Implicit in this is that if I have a set of elements and the first one is different and then the next one's all the same and the first one has relatively prime coefficients with everything else, I can replace x1 with this new element without changing the span. Okay, let's try to build some intuition. Let's look at some 2x2 matrices. So let's take numbers that are relatively prime. So let's say I take 3 and 4. Can you expand this out to a matrix where the determinant is either 1 or -1? Because if the determinant is 1 or -1, I can invert the matrix, and the inverted matrix will also have integer entries. So can you find something to put in so that the determinant will be 1 or -1? Yeah, 1, 1, right? Almost like I was being nice to you, right? If I do that, the determinant is going to be 3 minus 4, which is -1. Another nice one to do would be 2, 3, and then the determinant is 9 minus 8 is 1. Imagine I give you xy and the GCD of x and y equals 1. As soon as I tell you the GCD equals 1, what should you immediately be thinking of? Euclidean algorithm. So by the Euclidean algorithm, there exists A and B such that AX plus BY equals 1. So what I could do is I could put an A in the bottom right and a negative B in the top right. And now I will get the determinant is AX plus BY or 1. So what this is telling us is if I have a vector with integer entries that are relatively prime, I can extend it to a 2x2 matrix that's going to have determinant 1 or negative 1. What if I give you now let's say I give you a 3x3 matrix. What if I give you A, B, C, oh no, I'll do X, Y, Z. X, Y, and Z. And the GCD of X, Y, Z equals 1. What can we do? What do you think is true here? Yeah, so there's the extended Euclidean algorithm. There exists A, B, C such that AX plus BY plus CZ equals 1. So we have not proven this. It's a really good exercise to prove this. You know, use parentheses and grouping to do in general. But the Euclidean algorithm works for 2 elements. We can come up with a Euclidean algorithm for 3 elements, and so on and so on and so on. I'm not concerned with the most efficient way to find A, B, and C, just that there exists A, B, and C. One of the reasons the Euclidean algorithm is so great is it gives us a fast way to find A, B, and C. But right now, I just need to know that something exists. Well, unfortunately, a 3x3 matrix is much harder to work with. I don't quite know. So how do I use the fact that there exists an A, B, and C to start filling this in and make a matrix that's going to be invertible? Because when you take the matrix product, it's much more complicated. Right, but that's going to get complicated in terms of
for the later cases.
right, and so even at the 3 case, I think it's going to be bad. The trick is not to put it as a column, but to put it outside as A, B, C as a row vector. And the idea, if we have A, U equals V, where A is an n by n integer matrix with determinant equal to plus or minus 1, then this is equivalent to A inverse V equals U. What is AU? AU is some combination of the columns of A. A inverse V is some combination of the columns of A inverse. So because A is invertible, you give me any V, I can find a U such that AU equals V. You give me any U, I can find a V such that A inverse V equals U. We're assuming. So, right. So if the determinant is plus or minus 1, then A is invertible and it has an inverse with integer entries. So A inverse exists and has integer entries. Okay, so the goal is, and this is a really beautiful idea, is we're going to do some linear algebra. So again, the goal is to try to show you that the classes you took were useful. That there was a reason why we had you take that stuff before taking abstract algebra, okay? I'm going to find two matrices X and Y, such that Y transpose X is going to be the following upper triangular matrix. So it's ones on the diagonal, it's gobbledygook in the upper right, and then it's 0 in the bottom left. What's the determinant of an upper triangular matrix? Yeah, if I give you an upper triangular matrix, what is its determinant? Yeah, it's just the product of the diagonals. And so since the diagonals are all 1, it's 1. So what this means is if X and Y are integer matrices, the determinant of a product is the product of the determinants. Since the determinant is 1, then that means the determinant of X and Y is plus minus 1, which means X and Y are both invertible matrices. So this is how I'm going to construct my matrix X and prove that it's invertible with integer entries. We're going to do it, vector by vector. So we're going to start off by swapping out for our problem X1 with G, and then we're going to keep putting in new combinations so that we have the same span. So I'm not going to go through all the details of the linear algebra. I want to just do enough so that you can see if you really cared, you could do it. Now, when we look at the vectors X2, we know what X1 is, right? That's the vector G that we want to work with. Now we have these other vectors, X2 through Xn, Y1 through Yn. Is there anything we know right now? Any one of these vectors we know? Nope. Given X1, so it has relatively prime coordinates. What did we just show we know? Well, what do we know? If I give you a vector of relatively prime numbers, yes?
That we can multiply these primes or and get n once.
So we use what? Use the Euclidean algorithm. So gives us a Y1 such that Y1 transpose X1 is going to be 0. Oh, not 0. 1. So because of the Euclidean algorithm, we know there is a Y1. So you give me an X1, I've got a Y1, it starts the process. And so that's the next step. We're going to go by mathematical induction. And so the key starting point, key input is the generalized Euclidean algorithm. We just need the existence, not necessarily constructiveness. We don't necessarily need to be able to construct it. It's nice to be able to, if we want to specifically write down the matrix, then we better be able to find this vector Y1. And so the Euclidean algorithm just tells you that something exists. It turns out that when you generalize the Euclidean algorithm, in a shocker, you can do it in such a way that you can write down what the entries are. Depending on how you generalize, you might not have the fastest way to figure out what they are, but okay. So the last thing to do is to basically just say that we're going to go by induction. So assume we've done it for the first k x's, x1, x2, all the way up to xk. And then we can find y1, y2, all the way up to yk. And now we need to find the next one. And so what we're going to do is we're going to let A be x1 through xk. Now, these x's have n entries. So this is an n by k matrix. So when we look at the column space, what is the column space? It's k-dimensional. The column space is not everything, right? If I only have two columns, I can't generate an n-dimensional space. The columns live in Zn. I'm not able to get everything because I only have two columns or three columns or whatever. So clearly the column space isn't everything. So I was talking with somebody earlier today about the difference between range and image. Some people use them interchangeably, some people use them slightly differently. You know, the image is what is actually attained. The range is what is possibly attained. If you go into higher mathematics, they sometimes remove those distinctions and might have image and range the same. They talk about domain and codomain. Let's just talk about what is obtained, what is not. If I look at k columns, if k is less than n, I can't get all of Rn. I don't have enough dimensions. I only have k things. So clearly, the column space of A is not everything. And this is where you need to use linear algebra. And when you're looking at certain things, you know, the column space and the row space are related. And so because the column space is not everything, if I look at the equation yk plus 1 transpose A equals 0, can I find a vector such that this will be the 0 vector? Yes, because I'm not everything. Another way of looking at this is, if I look at the rows, can the rows be an n-dimensional space? Yeah. If the column space is k, what's the dimension of the row space? Well, so if I give you a matrix and I tell you the column space is k, what's the row space? What's the relation between the row space and the column space for a matrix? So if I give you the matrix, say, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I look at this, twice the second column equals the first plus the third, right? So the column space is only dimension 2. If I look at the rows, twice the second row is the first row plus the third. They have the same dimensions. If I look at 1, 2, 4, 5, 7, 8, the column space is clearly dimension 2. What about the row space? What's the dimension of the row space? Well, 1, 2, and 4, 5 aren't in the same direction. So the row space has a dimension at least 2, and it can't be more than 2. So you should have seen in linear algebra that the row space and the column space have the same dimension. So since the column space isn't everything, the row space isn't everything, I can find some vector yk transpose. If you don't like this, this is basically equivalent to A transpose yk plus 1 equals a different 0 vector. And now I'm looking at, finding something in the null space of A transpose. So if you don't like having a row vector on the left of your matrix, look at it instead as it's a column vector, but now you're applying it to A transpose. And so what this is basically just saying is the null space of A transpose is non-empty. I don't have full range yet. The null space is only the 0 vector if the column space is the whole space. And the column space is not the whole space. So I can find a non-trivial vector y. This is linear algebra. Does this seem vaguely familiar? Vaguely. But I'm just saying I've got something non-trivial in the null space. So we have a non-zero vector in the null space of A transpose or the kernel of A transpose if we want to use the more group theory terminology. No matter what matrix I give you, the matrix always sends the zero vector to the zero vector. Does it ever send anything else to zero? If yes, then the null space is not empty. The null space is all vectors sent to zero. And so we have a non-trivial vector y where we're basically sending it to zero. It's possible that the elements of y are not relatively prime. It's possible that the elements of y have denominators. They just have to be rational numbers. Because when we do the Gaussian elimination, A has integer entries. When we do all these calculations, we could get rational numbers coming into play. So the entries of yk plus 1 are rational. Interesting. It's no longer showing all the text. Okay, I was about to write hi, Mom. Oh, well, I'll still write hi, Mom. I said I would do it. Okay, so the entries of y, we can easily assume that they're integers. Do they have to be relatively prime? No, but what can we do? Yeah, we can divide. If entries are not integers, I'm sorry, relatively prime. If entries are not relatively prime, divide by the GCD. And this essentially finishes the proof, showing us that we can start off with x1 through xn, we can replace x1 with g, and then we can just keep going down and keep replacing things, and we'll have a new set of size n of objects that span the same thing as before, but one of them now has a smaller order, and that's a contradiction. And so to prove this, we needed a result from linear algebra. This is a nice result involving matrices. It's a nice way to show that we can find an inverse, that we can construct. There are so many things you can cover in linear algebra. If you haven't seen this, it's not surprising. Linear algebra, multivariable calculus, there's so many things to cover, you have to make choices. But it's nice to be able to see how some of that material could be of use here. So this is a good place to stop. And again, for the last 2 lectures, I really want to keep focusing like we did today on applications of what we've done, not just in this class, but in other classes you've taken, as well as what might you see if you continue with the math major and take some further classes. Where does this all go? But we saw a lot of stuff from linear algebra and multivariable calculus coming into play today. We saw some stuff from probability and combinatorics. And we saw one of my favorite problems where the optimal strategy is not even close to what you would expect to happen. It's not hopeless. And ending on things not being hopeless is probably not a bad idea. All right, so I will